Welcome to The Explainer. Today, we're diving into an essay that makes a really provocative claim that a lot of modern math and physics is built on what the author calls a fundamental cheat. The argument is that big ideas like curved geometry and complex numbers are basically just a smokescreen. So the author, Mathis, kicks things off with this zinger from Nikola Tesla. And this quote is really the launchpad for his entire argument. The idea is that math can get so abstract, so caught up in its own equations, that it completely loses touch with the real world. And that's exactly what he's accusing modern math of doing. Now, the central accusation here is pretty subtle. He's not saying that non-Euclidean geometry is flat out wrong. What he's claiming is that its complexity is used as a cover, a way to hide bad math and to push through proofs that just wouldn't hold up under simpler, more direct analysis. To get his point across, he does something pretty clever. He rebrands the terms. So forget Euclidean and non-Euclidean. He wants you to think in terms of straight versus curved. His argument is that straight geometry is the basic, transparent foundation. Curved geometry? Well, that's a secondary system that's not only less efficient, but also, he claims, way easier to fake. And here's where it gets really interesting. Mathis actually uses a quote from Henri Poincaré, who's often called one of the grandfathers of non-Euclidean math, to back himself up. Even Poincaré admitted that straight, or Euclidean geometry, is the simplest and most convenient. For the author, that's a huge admission from the other side. Okay, so let's get into his first major piece of evidence. The claim is that curved geometry doesn't just change the shapes, it actually introduces a flaw so deep that it makes the very idea of a number, well, stretchy and unreliable. The whole argument really boils down to this one simple but kind of mind-bending question. If the number 1, the fundamental unit of everything we count, can actually change its value, then what happens to the certainty of math itself? Think back to the geometry you learned in school. In that world, in straight geometry, the rules are rock solid. The shortest distance between 2 points is one single unchangeable line. The angles in a triangle always add up to 180 degrees. Period. No exceptions. But the second you step into curved geometry, all that certainty just goes out the window. The path between 2 points isn't a fixed line anymore. It's a curve. And as the author points out, you can draw an infinite number of different curves between those 2 points. All of a sudden, the length of a side isn't a fixed value. And this is where he lands the punch. The author argues that our very definition of the number 1 is tied to that unchangeable straight line. So if you swap that out for a curve that can bend and stretch, well, then the unit itself loses its meaning. The number 1 isn't just 1 anymore. It's become a variable, a fudge factor hiding in plain sight. All right, moving on to his next target. This time, it's another cornerstone of modern math, complex numbers. Mathis claims the way these numbers are usually derived isn't a real proof at all. He says it's just a series of confusing magic tricks designed to hide what's really happening under the hood. And, he really doesn't hold back his feelings on this. He sees the standard textbook proof for z equals x plus y as a chain of nonsensical steps. So let's walk through his breakdown of the so-called magic. Okay, so things start out simple enough. Your standard textbook will define a complex number, z, as just an ordered pair of real numbers, x, y. You can just picture it as a single point on a graph. No problem there. But here's the first move he flags as a trick. A regular number, like 1, is suddenly rewritten as an ordered pair, 1, 0. He asks, wait a minute, what does that 0 even mean? He says it's just an arbitrary decoration that's being added to set up the next bit of trickery. And then there's this. The ordered pair x, y, which, remember, is just a single point, is suddenly broken apart and written as the sum of 2 other points. For the author, this is a huge red flag. A location on a map isn't a sum of other locations. It's a move, he claims, that has zero logical justification. Next up is what he calls equation finessing. That term 0y is magically rewritten as a multiplication of 2 other pairs. Again, he argues this comes out of nowhere. It's just shuffling symbols around in a way that isn't explained, all to force a specific outcome. And after all that shuffling and substitution, we get the famous final form. The little ordered pair, 0, 1, is just assigned the value of I, the imaginary number. His conclusion? The whole thing is a house of cards, built on a foundation of these weird, unjustified logical leaps. So, after picking all of this apart, Mathis drops a bombshell. He claims that when you reverse engineer the math, the whole derivation is only actually valid if there's a hidden assumption all along, that x has to equal y. And if that's true, it would mean the imaginary number I is just a decoy, a distraction from a much simpler reality. Which, of course, leads to the big question, why? Why would mathematicians and physicists go to all this trouble to create such a confusing system? Well, his answer is that this complicated math isn't just a cheat, it's a smokescreen to hide something very real in the world of physics. He argues that this deliberately opaque math lets physicists use equations that work, they spit out the right answers, without ever having to actually explain the physical mechanics behind them. And what specifically is being hidden? He claims it's a real physical charge field, and that this math buries the mechanics so deep that no one ever thinks to ask the hard questions. And all of this brings us to his final verdict. It's really a call to go back to a different way of thinking, a standard of proof that puts clarity and transparency way above raw complexity. You see, for Mathis, a proof that's 200 pages long isn't some triumph of genius. It's actually a failure. The whole point isn't just to get an answer. It's to provide an explanation that's elegant and clear. He believes the real art of math is in making complex things simple, not the other way around. And to show what he thinks of the mathematical establishment, he brings up the intense backlash the columnist Marilyn Vos-Savant got for daring to question a famous 200-page proof. To him, this wasn't just a healthy debate. It was proof of a closed-off, almost cult-like field that attacks anyone who asks for a simpler explanation. And in the end, the author leaves us wrestling with this really provocative question. It forces us to ask what it actually means to prove something. Is knowledge something that should be clear and accessible to all? Or is it okay for it to become so complex that only a tiny handful of specialists can ever truly understand it?